In the previous sections in Chapter 4, we've looked at situations where we had constant coefficients, but in 4.7, we're going to transition to the situation where we have coefficients that are not constants. So in general, we have a term that's got a second derivative in it, some function of t with our first derivative, another function of t times our function, and then we could either have a constant, we could either have 0 on the right side, or we could have some function. So p of t and q of t are going to be variable coefficients of our function, our derivative, and our second derivative. Instead of in all the other sections in this chapter, all these coefficients, we might have had a coefficient here, those were all constants. So the first type we're going to look at is a very specific one, and it's known as the Cauchy-Euler equation. So in the Cauchy-Euler equation, it's going to always be in the format a t squared y double prime plus b t y prime plus cy equals f of t, where f of t could either be 0 if it's homogeneous, or it could be a function if it's non-homogeneous. And for this particular equation, our solutions are going to be in the format t to the r. Now remember, when our coefficients were constants, our solutions were in the format e to the rt. But when we have variable coefficients of this specific type, our solutions are going to be in this format, y equals t to the r. And very similar to y equals e to the rt, we're going to be solving a characteristic equation to help us find out what r needs to be. So let's look at why this is going to work. Since this is our variable to a constant power, then to take the derivative, this is just the power rule. So when we plug this in, we have t to some power. When we take the derivative of this, our power goes down 1, but then we multiply it by t, which makes our power go up 1. So these are going to have the same power. If they have the same power, they're like terms, so we can add those together. Same way, when we take the second derivative of this, our power is going to have come down by 2, so our power is going to be 2 less. But if we multiply that second derivative times t squared, that's going to make the power go up 2, so it gets us back to t to the r. So when we take our first and second derivative of this general solution and plug in, then each term is going to be something t to the r power. So they're all going to have the same exponent. So they're going to be like terms, which will add together nicely. So let's just do this generically and see if we can generate a method for solving for a, b, and c. So if y is t to the r, to get y prime, we would bring down our exponent, and then we would subtract 1. So that's y prime. Notice in that middle term, we have t times y prime. So if we do y prime times t, we would have t times r times t to the r minus 1. Since those are like bases, when we multiply those, we add the exponents. So r minus 1 plus 1. The minus 1 plus 1 will cancel, and that'll leave us t to the r. Now to get the second derivative, we go back to the first derivative, and we take the derivative of it. R is a coefficient, so we bring the power down, t to the 1 less power. So that's the second derivative. So to get t squared y double, we do t squared times what we got for our second derivative, which is r times r minus 1 times t to the r minus 2. Again, those are like bases, so when we multiply, we add our exponents. R minus 2 plus 2 minus 2 plus 2 cancel out. So we have our coefficients, and then we have t to the r. So if we substitute for t squared, y double prime, t, y prime, and c, and we're going to start out by solving the homogeneous situation, I guess. We're going to have a r times r minus 1, t to the r, plus b, and for t, y prime, we put in r times t to the r, plus c times y is t to the r, and we're going to do the homogeneous. So notice each term has a t to the r, so we can factor out t to the r, that, and let's go ahead and multiply that out. AR, so AR squared, AR times minus 1, so minus AR. If we factor the TR out, we're left with a BR. And if we factored out the T to the R, we're left with a C. So let's simplify the inside. Let's collect like terms. So we have an A to the times R squared. These are both R terms. So if we combine these coefficients, we have a B minus A. That's the coefficient of R. Then we have a plus C. So the only way this can equal 0 is this inside part equals 0. If t is non-zero, then we can't take a non-zero number, raise it to a power, and get 0. So this is our characteristic equation. A r squared plus b minus a times r plus c equals 0. Now remember, that's the characteristic equation for a squared y double prime b t y prime plus c equals 0, cy equals 0. So the a, b, and c come from the coefficients that accompany the t squared, the t, and the constant coefficient here. So let's work through an example. So let's do this one. Let's do t squared y double prime plus 5t y prime plus 4y equals 0. So our a, that's the coefficient of t squared y double prime, is 1. B is the 5. C is the 4. So if we set up our characteristic equation, it's this. Let's just copy that over. A r squared plus b minus a r plus c equals 0. So we substitute in our a. We substitute in b and a. Substitute in c. So we have r squared plus 4r plus 4 equals 0. Now if we factor that, we get r plus 2 times r plus 2 equals 0. So r equals negative 2, and that's a double root. Remember, our generic solution was y equal t to the r. Here, if we have a double root, then we have a t to the r as one solution, but as our second solution, it's a little bit different than when we had e to the rt. For our second solution here, we have t to the negative 2 natural log t. So if we have a repeated solution, a double root, that solution becomes our r, but to get our second solution, we still have that same r, but we pick up a natural log t. What if we have a complex solution? If we have a complex solution, if r is, let's say, alpha plus beta I, then y equals t to the alpha plus beta I is our solution. So y equals t to the alpha, t to the beta I. And recall what we saw before when we had e to the I theta. If we have e to the I, we simplify that as cosine theta plus I sine theta. Well, we can write this t to the bi as e to the natural log of t to the bi. Remember, when we have e to the natural log, since these bases are the same, they undo each other. So with a little clever algebra, we can move that bi out front. And let's call that, instead of bi, let's call it I times b natural log t. So for this part, that becomes cosine of b natural log t plus I sine b natural log t. And then we still have our t alpha in front of it. So we have t alpha times cosine b natural log t, t alpha times I sine b natural log t. And remember, we also have these unknown coefficients that go with it. So our homogeneous solution will be C1 t alpha cosine beta natural log t plus C2. The I is going to get engulfed into the unknown coefficient. So t alpha sine b or beta natural log t. So that's what happens if R is complex. If R is a double root, we get one solution, t to that power, we get another solution, t to that power, and to get the second independent solution, we pick up a natural log t. If we have two separate solutions, let's just call them R1 and R2, then one solution is t to the R1, the other solution is t to the R2. So in general, for our homogeneous solution, we would have C1 t to the R1, C2 t to the R2. So it's similar to what we had in the past once we got the solutions to our characteristic equation. If we had separate solutions, we would just plug into our R's for our R's. If we had complex solutions, we would have a real part and an imaginary part. So our real part would be our exponent. Just like when we had e to the RT, our real part was the R. And then the imaginary part would be our coefficient of cosine, our coefficient of sine. But since this is a solution for a Cauchy-Euler, then we have a natural log that goes with that. So that's how we solve a Cauchy-Euler equation. So let's do a quick reminder of a few things that still apply, that if we have solutions to a second order differential equation, so here's our general second order equation. So if y1 and y2 are two solutions to this on some interval I, then remember the way we checked to see if y1 and y2 were independent was by what we call the Wronskian. And the Wronskian is simply y1 times y2 prime minus y1 prime times y2, or in determinant form, y1, y2 in the first row, y1 prime, y2 prime in the second row. So think about it. If we multiply our determinant, we multiply diagonally this way minus diagonally this way. So that's our Wronskian for y1, y2. So what does that mean? If this is 0, then y1 and y2 are dependent. If it's not 0, then they are independent. So the book goes on to say, says just as in the constant coefficient case, the Wronskian of two solutions is either identically 0, meaning it's always 0 on that interval I, or it's never 0. So if it's never 0, then y1 and y2 are independent. Also, just as in the situation where we had constant coefficients, when we have our second order differential equation, the homogeneous C1y1 plus C2y2 is a general solution for our homogeneous. And then our general solution for the non-homogeneous is the solution to the homogeneous plus the solution to the particular. So remember how we get the solution to a particular. When we set up this with with constant coefficients, we came down with two equations. We said that the particular solutions were going to be in the format some function times y1 and some function times y2, where y1 and y2 were solutions of the homogeneous. So once we took our derivatives of that, plugged in, and so forth, we said that, and they wrote it in a different order. They call it y1 v1 prime plus y2 v2 prime. Remember, we set that equal to 0 so that we wouldn't, when we took our second derivative, we wouldn't have a second derivative of v. We would just have a second derivative of y. And then our other equation was y1 prime v1 prime plus y2 prime v2 prime equals g, where g is what we have on the right side. So if it's not homogeneous, then the function on the right side will be called g. So that's our function on the right side. So they gave us a formula that v1 in general is the integral of minus g times y2 over the Wronskian dt, and v2 is the integral of g times y1 over the Wronskian dt. And really, this is just, remember, if we solve this system for v1 prime, we could do that using Cramer's rule or whatever. This is essentially the solution, the inside part, that is, if we solve for v1 prime, that's what the solution for this system of equations using Cramer's rule. Remember, the Wronskian is the determinant of the coefficients on this side. That's what we divide by. Minus g times y2. If we replace the coefficients in the first column with 0 and g, we would get that when we took the determinant of the left side. Down here, if we replace the coefficients in the second column with 0 and g, this is what we would get when we took the determinant of it. So the Wronskian is just the determinant before we replace these columns with 0 and g. This is what the determinant when we replace the first column with 0 and g, and this is what we get when we replace the second column with 0 and g. So that just comes from Cramer's rule. So this is V1 prime, so to get V1 we integrate it. This whole thing is V2 prime, so to get V2 we integrate that. So these general solutions and the way we get our particular solutions to the non-homogeneous using this system of equations, using the Wronskian, this is applicable to all second order differential equations, whether we have constant coefficients, whether we have variable coefficients, and the only variable coefficient specific type that we've done so far is Cauchy-Euler, but this will apply to any, whether they're Cauchy-Euler or not. So in this section, most of the ones we do with variable coefficients will be Cauchy-Euler, but occasionally we might have some that don't fit that format. So if they don't fit that format, then sometimes we use a process known as reduction of order. So in reduction of order, we know one solution, and we're wanting to use that solution to find the second solution. And when I say the solution, we mean for the homogeneous. When we did Cauchy-Euler, when we did constant coefficients, we were able to find both solutions to the homogeneous. But sometimes we end up with some differential equation that might not be Cauchy-Euler. For example, y double prime minus 1 over t y prime plus 1 over t squared y equals 0, which this one actually, if we were clever, we could possibly turn this into Cauchy-Euler. But if we knew one solution to this, we could end up finding a second solution. So we're going to suppose that the second solution is related to the first solution by multiplying it by some function. If we work through this correctly and substitute that generic solution into our differential equation, then we should come up with a differential equation that is separable. And if it's separable, then we've in the past looked at how to solve those particular differential equations. So let's look at this generically, and then we'll come back and look at it more specifically. So if our second solution is of this format, then let's get the derivative of that. If we take the derivative, we have to use the product rule. So the derivative of the first times the second plus the first times the derivative of the second. And then to get the second derivative, we have to take the derivative of that. I don't know how this became a y double prime. That was supposed to have been, wow, I botched that. Let's go back. I was thinking about right in my head, but I said it wrong. To take the derivative of that, it's the derivative of the first times the second plus the first v1 times the derivative of the second. So now to get the second derivative, we need to take the derivative of what we have there. So when we take our second derivative, it's the derivative of the first term. That's a product rule. So it's the derivative of the first. So v1 double prime y1 plus the first term times the derivative of the second one, y1 prime. So that's the derivative of that one. Now we have to do the derivative of that. So plus the derivative of the first factor, v1 prime times the second one, plus the first term, or I keep on saying term, the first factor times the derivative of the second one. And if we combine like terms there, we have a v1 double prime and a y1. We have a v1 prime, y1 prime, another one of those, so we have two v1 prime, y1 primes. Then we have a v1, y1 double prime. So if our general differential equation is y double prime plus p y prime plus q y equals 0, then we can substitute in v1 double prime plus 2 v1 prime y1 prime plus v1 y1 double prime. That's y double prime plus p times excuse me, y prime. Y prime is v1 prime y1 plus v1 y1 prime plus q times y, and y is v1 y1, and that equals 0. Now what we're looking for is v, so we can rewrite this, reorganize this in terms of v, and we notice we only have one v. We don't have a v1 and a v2 really, so all of these v's we can just call v instead of v1. And let's organize these based on the level of their derivative, whether it's v2, v double prime, v prime, or just v. So we have a v double prime y1. We have, let's change colors, we have a v prime there. We have a v prime there. So our coefficient of v prime is, let's see, 2 y1 prime. If we distribute that p, we're going to have a p times y, 1. So that's our coefficients of v prime. Now our coefficients of v, let's see, we have a v here that's got a y1 double prime. We have a v here, so if we distribute that p, we have a p y1 prime. And then we have a v here, so we have a q y1. And then we have a 0 on the other side. So let's make an observation. So our original equation, that's our general differential equation. And y double prime plus py prime plus qy, that's equal to 0. Notice we have a y double prime, py prime, qy. So that is 0 from our homogeneous equation. So that simplifies us to v2 prime y1 plus 2 y1 prime plus p y1. That's the coefficient of v prime, and that equals. Now this is a second order differential equation where when we were doing separable, that was a first order differential equation. So let's make a substitution. Let's replace v prime with w. That means v double prime is w prime. So out front, let's call this y1 w prime, and then we have 2 y1 prime plus p times y1 w equals 0. So w prime and w there, so this is first order. We're looking for w, because if we get w, then we can get v. So this is a first order, and it does turn out that this is going to be separable. Without showing all the rest of the painful steps, it turns out that our second solution comes from taking the first solution times the integral of e to the negative integral of p of t dt over y1 of t squared dt. This is y1 of t. So this top part should look familiar. This is our special integrating factor when we had first order differential equations in the beginning. So whatever our p is, integrate that becomes the power of e, divide by our first solution squared. Once we divide that, integrate it with respect to t, and then multiply that times y1, that will give us our second solution. But instead of using the formula, sometimes we'll just use our technique that we use to establish that this was indeed a separable differential equation to actually find our solution. So let's work through an example and see how that goes. So let's look at the one I mentioned a minute ago, y double prime minus 1 over t y prime plus 1 over t squared y equals 0. And we're given that one of our solutions is simply t. If we take the first derivative, the derivative of t is 1. If we take the second derivative of that, we get 0. So 0 minus 1 over t times 1 plus 1 over t squared times t equals 0, and that's true. T over t squared, that reduces to 1 over t. 1 over t times 1 is 1 over t, and those do make 0. So, yes, indeed, that one is a solution. So, knowing that solution, we want to find another solution. So then we suppose that a second solution comes from some function of t times t. So let's take our first derivative. So the derivative of v times t plus v times the derivative of t. So v prime t plus v, that's our first derivative. Now we need to do our second derivative. So our second derivative is the derivative of this. So the derivative of v prime is v double prime times t plus v prime times the derivative of t, where the derivative of t is 1, plus the derivative of the next term. So the second derivative is v double prime t plus 2v prime. So let's take these and substitute into our differential equation. So for y double prime, we have v double prime t minus 1 over t times y prime. So y prime is v prime t plus v plus 1 over t squared times y, which our y is v times t, and that should equal 0. So if we distribute plus 2v prime, when we multiply those, the t and the t's cancel, so we get minus v prime. When we distribute there, we get minus 1 over t times v. And then when we multiply here, that t cancels one of those, and we get 1 over t times v equals 0. If we simplify this, we have basically a v over t here and a minus v over t here. Those cancel. We have a 2v prime minus 1v prime, so we have, let's call this t v double prime plus 1v prime equals 0. So let's make a substitution to simplify this to a first order differential equation. So as we did in the derivation, let's replace v prime with w, and therefore v double prime with w prime. So we get t w prime plus w equals 0. Keeping in mind that w prime is dw over dt. So we should be able to separate this and integrate this. Now keep in mind that when we integrate this, when we get a constant, an arbitrary constant on the end, we're just going to treat it as 0 to make our integration simpler, since we don't have an initial value. So we can move the w over, dw dt equals minus w. We could move the dt and the t over, so that would give us dt over t, and we can move the w to the other side, so that would give us dw over minus w. So now if we integrate both sides, we can pull that negative out front, integrate here. So we have negative natural log w on the left, natural log t on the right. Let's move the negative to the right side. So natural log w equals negative natural log t. Or keep in mind that's a negative 1. So natural log of w equals natural log of t to the minus 1, or 1 over t. To get w, we can do e to both sides. So e to the natural log undoes itself, so that's w, which remember w is the v prime. E to the natural log, that gives us 1 over t. So then if we want to get v is the integral of 1 over t dt, which when we integrate 1 over t dt, we get natural log of t. So our second solution, remember, is v times y, so natural log of t times y1, which y1 was t. So v2 is t times natural log of t. Now, if we go back and look at our equation, if we multiplied everything by t squared, we could have converted that into a Cauchy-Euler. We would have had t squared y double prime minus 2t y prime plus y equals 0. If I remember that correctly. Am I missing a number? Let's see, I'm not supposed to have a t there. Yeah, so there wasn't supposed to be a 2 there. So if we would have solved this, this would have been a Cauchy-Euler where a is 1, b is negative 1, c is 1. So our characteristic would be a r squared plus b minus a, so minus 1, so minus 2r plus c equals 0. If we factored that, remember a is 1, we'd have had r minus 1 equals 0, so we would have gotten r equals 1 as a repeated root. So our y1 would have been t to the first power, our y2 would have been t to the first power natural log of t, which is exactly what we have. We have y1 being just t, y2 being t natural log t. So this was a longer way to get there, but this would work whether this could be rewritten as the Cauchy-Euler or not. If we have non-constant coefficients and we know one of the solutions, then we can use this process of taking that solution times a generic function v, and that being our second solution. So take our first derivative, our second derivative, plug in, we will end up with a separable differential equation and solve that so that we can get v. Once we get v, our second solution is v times y1.